Okay, let's begin. Everybody's doing trig now. So, we're going to continue the story of trigonometry. Last time was an expose. We'll continue that now. We'll do a few examples, but we'll mostly be doing examples towards the end, I guess. Right now we want to just build it up, see where all these ideas we're using come from. So, 5.1, 5.2, 5.3, continue. So, what did we talk about last time? Recall. We developed two trig functions. We had functions sine of theta and cosine of theta. And the point of these two functions were to track the coordinates on the unit circle. Circular radius 1, centered at the origin. And if we measure an angle theta, then and we let a line running through that angle hits the circle, the coordinates of that point will be given by cosine theta, sine theta. So the x value is cosine and the y value is sine. And so we're tracking the x's and y values separately here. This is like a y and this is like an x. And why is tracking the unit circle such a big deal? Well, for many reasons, you'll also see in future classes. We'll do some stuff on trig in Calc 1, but mostly in Calc 2 for those of you who are going that far. You'll start to see where trigonometry becomes really useful. Sometimes we can, instead of looking in rectangular coordinates in x and y's, we can look at things like theta and r. So if we have some random point over here, there are two ways to think about it. We can think about the x and y coordinate that give us that point, or we can think about an angle and a distance that makes that point lie on a circle. And just by that change of point of view, you can make a lot of problems a lot simpler. So in the same way that we came up with logarithms to make certain calculations simpler, trig functions also can make a lot of calculations simpler. That is way in the future though. Right now we just want to actually study these functions and learn what they're about. We also saw that we defined some other functions in terms of their ratios. So tangent was defined as the sine divided by the sine function divided by the cosine. We saw that the secant was 1 over the cosine. We saw that the cosecant was 1 over the sine function, and we saw that the cotangent was 1 over the tangent function, which you can think of as cosine over sine. Notice that if whenever I'm writing sine or cosine, I do write an angle beside them. It makes no sense to have them on their own, so be careful of that. You have to be operating on some angle. The angle is the input, the sine function or the cosine function will give you an output. Specifically, it will give you a coordinate on the unit circle. We also saw Sokato. For some reason, I always have the urge to say that in like a Japanese karate movie. Sokato! That's what I think. I don't know why. But this is for sine. The sine of theta is the opposite over hypotenuse, and the cosine of theta you can think of as the adjacent over hypotenuse, and the tangent of theta is the opposite over adjacent, where these sides are defined as follows. And again, there was a natural way to actually draw a rectangle, which we saw that we could do in the circle. just by looking at this line as the hypotenuse and doing it down and across. And just by thinking of this length here as the x-coordinate and that length here as the y-coordinate and using similar triangles, we could develop this idea here. So that allowed us to calculate some special angles. And what were the special angles and what are their values? So there was pi over 6, pi over 4, and pi over 3. Right? And we could figure out what these values are. Now originally we used SOHCAHTOA with some specially crafted right triangles to figure this out. But once we actually have that information, it's nice to encode it in a table where we can get the values pretty easily. And for sine, we count up from 1 to 3. For cosine, we count down 3, 2, 1. Take the radical of everybody, and then divide everyone by 2. And these are all the values of the sine and the cosine function at very specific angles. This one was equivalent to, and we're sort of going to move away from talking about degrees. We'll spend most of our time in radians. This one is equivalent to 30 degrees. This is equivalent to 45 degrees. This is equivalent to 60 degrees. However, as you'll start to see today, it's a lot more efficient to think in terms of radians. And so math people tend to think in terms of radians, while engineers and young children tend to think in terms of degrees. And a lot of people find it easier to think in terms of degrees, but this is familiarity. That's the only reason why it's easier. Once you actually get used to working in radians, you'll actually never want to go back. It's pretty easy working in radians. And we'll see some ways in which it's a lot easier to think about things in terms of radians today. So we got up to here around pretty much, and then I mentioned that the next thing we really want to talk about is the angles. So we got to a point where it was a very nice point to segue into talking about terminal angles and reference angles. So let's talk about that, why they're useful. So just a little bit of insight should be able to, you'll be able to notice the following. The sine and cosine are what we call periodic. That's a general phrase. That is, they repeat their values at regular intervals. It's not very hard to see. Let's say, okay, here we're on the unit circle. Here's some angle that I'm thinking about. Say it's like theta. So now the point of the sine and the cosine is, of course, to tell me about the coordinates at this point. But one thing you'll notice is if you were to measure an angle, but just keep going, go all the way around and come back and stop here, this will be a larger angle technically, but you'll notice that if I call this, I don't know, alpha, you'll notice that these coordinates would have to actually be the same. You'll notice that the values of the angles will actually repeat themselves because you're just going around in a circle. In fact, for every time you go around in a full circle, which last time we also learned was 2 pi radians, you'll notice that the values of the sine and the cosine will actually start repeating themselves. Right? So this means that there are essentially along a circle, you can actually measure angles any value from negative infinity to positive infinity, in fact. And however, there are always values that will be repeated. And so in general, so we say the period. That's the length of the interval that you need to go before you start repeating values of sine theta and cosine theta is 2 pi. That is, every time you increase your angle by 2 pi, you actually start getting the same values again. If you take sine of an angle, it's going to always give you the same value as sine of that angle plus 2 pi. In fact, you can keep repeating this process forever. You can just go around the circle one more time, around the circle one more time. So one way you can express this is it's equal to let's do that, and then in fact, let's say that this can keep going, plus 2k pi, right? The 2 pi itself is called the principal period, because that's the smallest value that you'd have to elapse to start getting the same values again. Here, k is any integer. So again, these functions were just tracking points on the unit circle, but there are multiple ways you can get to that point on the unit circle. In fact, we can start here and we can go the other way. And what does that mean? So let's talk about some convention there. So this is purely convention. Sine of an angle. Not the sine is not plus or minus sign of an angle. Indicates the direction in which that angle is measured. Specifically, we take the following convention.
Wait, what does that say in green?
Principal green.
No, right here on the first one where you're erasing. It says cos. What sign is that?
Cosine of alpha and sine of alpha. The green angle I called alpha, and the white angle I called theta. So specifically, we have a positive angle. This means it's measured counterclockwise. Okay? So for example, if someone tells you theta is equal to pi over 4, okay? This means on the unit circle, you start at the positive x-axis and you move until you cover an angle of pi over 4. Now by the conversion, you realize that pi over 4 is actually 45 degrees, so it actually should be like midway here. So this theta is measured as positive pi over 4 because it starts from is measured from positive x-axis. So you start from the positive x-axis, and then you start traveling in the counterclockwise fashion, and you keep going until you hit a certain theta value, right? And so that would be positive pi over 4, right? So I can write positive here for emphasis. And negative just means clockwise, means the opposite direction. Negative angle means it's measured clockwise. And again, from the positive x-axis. So you can talk about what does it mean for someone to tell you minus pi over 4 is the answer.
Yeah.
Well, here you have the unit circle. Start with the positive x-axis. Instead of going counterclockwise, you go clockwise. Go in the direction that the clock moves. That angle we can think of as minus pi over 4. So it's the direction in which you're measuring the angle. And that's just convention. Convention means it's just a rule that we all make up so that we can all get the same answers. And you start to see the reasons for why we measure positive going counterclockwise and negative going clockwise. When you get to physics, maybe if you're a math major, you probably start noticing in a class like 392 or something like that, because there are reasons in reality why we want to describe positive and negative this way, in terms of like how electric currents behave and all sorts of crazy things. Okay, but this is just the definition we take. Positive is measured counterclockwise, negative is measured clockwise. And we also notice that every time we go around a circle and kind of stop on the same line, we actually end up with the same coordinates. So this gives us that the sine and the cosine are periodic. They eventually repeat some values. Now this brings up what I want to talk about. Terminal angles and reference angles. And I don't want to get too technical here. I just wanted to explain the idea. Angle theta can be any real number. A given angle is called the terminal angle. The coordinate associated with this is the terminal point. So for example, I can talk about an angle theta, and let's say starts here. Let's say I want to talk about theta equals, say let's do 5 power 4. That guy's going to end up around here somewhere. We'll start to measure this pretty soon. For now, just take my word for it. That's where it's going to end up. And so this angle here, measured all the way around here, that's your theta. That's called your terminal angle. Now, if you're on the unit circle, that theta would be measured by this line, and this coordinate here on that circle is called the terminal point. Let's talk about the reference angle. So pretty much any angle you're given you can think of as a terminal angle, and you can talk about the point where you can stop measuring that angle. That's called the terminal point. For some theta, it's reference angle. So that's the technical term I'm going to define now. The usual notation for this is theta with a bar on top of it. This is the smallest angle theta makes with the x-axis. That's the definition. So, let me show you some situations. So there are pretty much 4 situations that you can be in, which I'm going to describe. So we can assume our reference angle, theta, is in the first quadrant. We can also assume, and quadrants I defined last time as well, defined a lot of stuff last time. We can think of our theta as being measured, again, from the positive x-axis to a line in the second quadrant. We can talk about theta as being measured from the positive x-axis to some angle in the third quadrant. That's your theta. You can also measure theta as some angle that goes all the way around to the fourth quadrant. So that's your theta. Now the reference angle doesn't care about the actual angle. The reference angle only cares about the smallest angle that you make with the x-axis. So in this case, if you look at the x-axis, what is the smallest angle that this line makes with the x-axis? Well, it's actually itself. So if you can talk about some angle that's in the first quadrant, your theta is between, and right here I'm just, for convenience, I just want you to get the idea. Here I am assuming that theta is between 0 and 2 pi. In that case, if you're in the first quadrant, your reference angle is the same as the actual angle. However, if you're in the second quadrant, think of the x-axis, here's the line. What is the smaller angle that you make? Well, it's now this angle over here. That's the smaller angle that you make with the x-axis. You'll notice that over here, you can do that same analysis, and you only actually care about this angle right here. That's the smallest angle you would make with the x-axis. If you're over here, it would be this angle right here. That's the smallest angle you would make with the x-axis. Now, for your theta in this region, you can actually quite literally compute what theta bar is, the reference angle is, compared to the actual angle. Here, of course, you'd see that, I don't know if I want to use a different chalk for this one. I have a lot of colors, so why not use it? Here you'll notice that for 0 to 2 pi, with your terminal angle in the first quadrant, you will have your theta is the same as the reference angle, theta bar. What do you think the angle would be here? How would you measure the reference angle in this situation?
180
Versus the reference angle in this situation versus the reference angle in this situation. Come again? 180. What do we do with 180? Right, so that's radians. In radians, that would be pi. So what is pi? Pi is actually this entire thing here. So notice that this entire angle is pi. This angle is theta. Your theta bar is just the leftover. So you take pi minus the theta. So if your theta ends up in the, if you can get your theta to be in the second quadrant, given that it's between 0 and 2 pi, your reference angle will just be pi minus that angle. What about here?
Theta minus pi.
Okay. So theta is all the way around here. We know that pi is this part. So if we take theta and subtract the pi part, we are left over this. So this is theta minus pi. This one, by similar reasoning, this will be 2 pi minus theta. Because to go all the way around is 2 pi. If you subtract the theta portion, you're left with the theta bar portion. Here are some important things to note. Why did we come up with this definition? Remarks. Given any angle, it can be expressed equivalently at least with regards to what the trig functions will do. with regards to trig functions. Find angle theta such that the theta is within this region here. And how would you do that? Well, by adding or subtracting multiples of 2 pi. That's the first important remark. So, for example, let's say someone tells you like 500 degrees. Let's start with degrees. Find theta equivalent to this. And find its reference angle. So, have your unit circle. Now a full circle has how many degrees in it? 360, right? And each quarter will have 90 degrees, right? And so this whole thing is 180 and etc. So you can start here, and you can start measuring your angle going all the way around. So you'll go all the way around, boom, and that's 360. Now how much farther do you actually need to go? Well, what you can do is you can take 500 minus 360. What would you get? Huh? 140. So now you can pretend you're starting from the beginning and measure off an additional 140. Now I know to go all the way over here is 180, so 140, it's definitely past 90, it's going to be over here somewhere. Okay? So now that's your 500 degrees. Now, in terms of trig functions, if I want to actually measure that angle in another way, I can come up with an equivalent angle called theta. And what would the theta be here? Well, it will actually be the 140. Right? I subtracted one multiple of 2 pi, which in this case is 360 degrees. And so this is equivalent to an angle measured like that in terms of a trig function, right? If I'm plugging into a trig function, plugging in 500 degrees and plugging in 140 degrees would actually give me the same value for the trig functions. That being said, here's a value that is it's larger than 90 degrees. I actually want the reference angle to that. So what would the reference angle be here? Well, this guy clearly ends up in the second quadrant. So I'll simply take pi minus that, which is going to be what? So it's 180 degrees minus 140 degrees. So it'll be 40 degrees. Which means my reference angle is going to be the guy here. And of course, if this were something larger, like 5,000, what I do is I just keep subtracting 360s until it will eventually hit 140. And then I can just do the reference angle calculation to think of it as 40. So that's one remark. Given any angle, in terms of the trig functions, I can find an equivalent angle. And I can think of this pink angle as the terminal angle, right? Once I find that terminal angle, which is between 0 and 360, depending on which quadrant it ends up, I can compute the reference angle. So that was one important remark. Now, why is it important to know what the reference angle is? The reference angle, you would notice, or hopefully you can get from the picture, the reference angle will always be an angle smaller than 90 degrees. Now it turns out that all the nice angles we know about are smaller than 90 degrees, right? 30, 45 degrees, 60, right? This gets us to within the realm that our table can start to tell us what values things are, especially if the numbers are nice, right? We don't know like you ask me, what is sine of 143 degrees? I don't know, you use your calculator. But sometimes it'll have very nice values or close to very nice values that we can actually start to approximate with our table values. So that's the next remark. So let's call that remark 2. So given an angle, I can find some equivalent terminal angle that is between 0 and 360. Given that angle, I can find its reference angle. Why is that important? Well, now we can just notice that since sine theta and cosine theta are periodic, and we have all students take track or calculus, or spoke about it last time, we can deduce the following. Given the sine of any angle, which I can get to be between 0 and 360, it's going to give me an equivalent value of sine evaluated at the reference angle. What's the difference? It can take a positive or a negative sign based on all students take calculus. Similarly with the cosine. I can actually compute the cosine of some angle by finding the equivalent angle that's between 0 and 360, then finding its reference angle and taking its value, and that will allow me to actually find this guy, where the sines are chosen based on the all students take calculus, right? The fact that this guy keeps repeating values means that, yeah, I can sort of try to cut down on any excess, and it won't actually matter when I'm plugging it into a trig function, as long as I cut down on the excess in a very strategic way. Like first, subtracting or adding multiples of 2 pi to actually get within 0 to 360, then finding its reference angle, these things will automatically take effect. Let's actually do some examples of using this idea. So this is something that's important. So we finally got to some examples that you can actually, well, we did some before. But here are some examples that will actually directly apply to things that you would be expected to do on a quiz or a test. So finally got to some. Actually, it took me a lot longer to get here than I thought. Like sometimes in my notes I just write bullet points, oh, just explain this to them. And in my head it's like, oh, it's going to take like 5 seconds to explain this thing. And it takes like 40 minutes instead. That's the challenge. Sometimes when you know something, the knowledge is just so complete in your head, but then you realize to actually say it out, it takes a really long time. Wow. I'm nowhere close to where I expect it to be at this point. Okay, anyway, let's continue. It's not a total disaster, so don't worry. Oh, I actually want to do some more of these examples, and then, yeah, but see, now that I told you that, this example just is pointless. Let's actually just skip to the second one. Examples. We'll just do a few. Find the following. Or maybe I want to do it anyway. Given theta, find theta bar. Just a little stepping stone. So that's the first example. A. Just gonna put some random numbers here. So theta equals this. Because this allows me to tell you about the nice thing about things like these guys. Do 1 degrees example. Two. Compute A. Let's do sine of 7 pi over 6 cosine minus 4 pi over 3 c sine 3 pi over 4. Now it turns out that these are values that you can actually find exactly. So we're going to tie all to everything that I've been explaining up until now. We'll bring them to bear on these problems. And in the first three, in example 1, you'll see a nice little feature about the special angles that we have when we're talking about the multiples of the special angles. What do you think the reference angle is for that? Pi over 4? How do you know? Did you actually do it? Just something that you know? Yeah?
If it was 8 pi over 4, it would be 2 pi.
Yeah.
So if you subtract the 2 pi from 7 over 4, it's going to be pi over 4.
That's a nice way to think about it. Very calculation-wise. Here's another way. Let's think of it as a picture, because thinking in radians, this is one way in which it's nice. You can get to use, and again, thinking in pictures is super important. Remember, once we learned how to graph things, math just took off. A lot of things are nice. But here's one thing you can notice. If you look at a unit circle, or any circle, it doesn't have to be unit. Okay? So let's say the origin is right here. Let's just put in the diameter. Now remember, we measure the angles positive going counterclockwise. So, and we always start with theta equals 0 on the positive x-axis. Now, once I go all the way over to here, what is the theta value?
Pi.
It's pi. So, one way you can think of the radians is the entire top half of the circle represents an angle pi. The bottom half also represents an angle of magnitude pi. Right? Now here's the nice thing. What you can look at here is you can isolate pi and the denominator, which here we notice it's a special angle, but it doesn't actually matter too much for the illustration here. What we see here is pi over 4. So when you see pi over 4, what do you think of?
45 degrees.
In terms of the picture, how would you look at pi over 4 on the picture? You divide pi into 4 pieces. That's what it means. So here's pi. Let's actually slice it into 4 equal pieces. Each of those pieces would be pi over 4. How do you slice something into 4 equal pieces? Well, slice it in 2 equal pieces, then slice those 2 into 2 equal pieces. Now we've sliced pi into 4 equal pieces. You can notice that you can actually do the same thing on the bottom. So thinking in terms of pi over 4s allows us to split the circle into 8 parts, 8 equal parts, where the angle in each part is pi over 4. Right? So what does 7 pi over 4 mean? Well, it means take 7 of these parts. So it means you can start here, and then you start counting. 1 slice, 2 slice, 3 slice, 4 slice, 5 slice, 6, 1, 2, 3, 4, 5, 6, 7 stops here. Okay? Now you'll notice that based on your definition of reference angle, that's going to be this guy. But how big is that guy? Well, it's obvious from the picture. It's pi over 4. I sliced it where each pizza slice is pi over 4. So I don't even have to think in terms of calculation. Oh, I have to subtract this from 2 pi. Just looking at the picture, it's obvious. Pi over 4 is going to be the reference angle. I can do the same thing again. So let's do theta equals 5 pi over 3. Guess what the reference angle is going to be? It's actually going to be pi over 3. Now, at first, you'd actually think about it as pi over 3. So what this means is, here's your circle, you slice it in 2, that's pi, that's 0. Now what I want to do is I want to take the top half and slice it into 3 equal pieces. So, something like that. Do the same thing at the bottom. What does 5 pi over 3 mean? Take 5 of these pieces. So you start here and you start counting. 1, 2, 3, 4, 5 also ends up over there. You'll notice that that's actually all again in the first quadrant. The reference angle is of course going to be the smallest angle to the x-axis. That's pi over 3. Again, very obvious from the picture. So if you can think in terms of the picture, in terms of radians, which will often have pi's in them, it tells you how you can slice up a circle. And then you can actually count off the pieces. At least the problems that you can do by hand, they're going to be like this, which is problems that we'll be doing. We're not allowed to use calculators here. Minus 11 pi over 6. Of course, spoiler alert, the reference angle is going to be pi over 6. But there's still benefit to think of the picture, which when we get to the next example, we'll see what that benefit is. Okay, so what would I do here? Draw the circle, slice it in half. That line represents pi. What do I want to do here? 6 equal pieces. How do I get 6 equal pieces? Well, I can slice it into 2, then slice each half into 3. So do the same for the bottom. Slice into 2, slice each half into 3. So now if I start here, I get to minus 11 pi over 6. Go clockwise because of the negative sign. So I'm still counting off the slices, but I'm going this direction instead. So, of course, 1, 2, 3, 4, 5, 6. I know 6 pi over 6s give me all the way to pi. 7, 8, 9, 10, 11. This one actually ends up in the first quadrant. So what's its reference angle? Well, it's the smallest angle to the x-axis. So it's pi over 6. In other words, in terms of trig functions, 7 pi over 4 I can think of as being somehow equivalent to pi over 4, 5 pi over 3 is equivalent to pi over 3, and minus 11 pi over 6 is equivalent to pi over 6, equivalent with a sign change. That sign change comes according to, all students take calculus. Now let's actually apply those ideas to this guy. Any questions on this? Because we're going to do this here. So if you don't understand this, you're not going to understand this. Questions over here? Example 2a. So if someone were to ask you, what is sine of 7 pi over 6? Here's what you're going to do. Well, I never memorized what is sine of 7 pi over 6. So far, I know what is sine of pi over 3, pi over 4, and pi over 6. I don't know what 7 pi over 6 is. However, based on the second remark, I know that that guy is just going to be equivalent to plus or minus sine of the appropriate reference angle. So now my goal is find that guy. So what I would do, I need to find sine of 7 pi over 6. I'm going to draw a circle. Well, of course, I want to slice pi into 6 pieces. So slice that into 2, slice each half into 3. Slice that into 2, slice each half into 3. Start here, that's a positive angle, so I'm going to go counterclockwise, and I'm going to count off 7 pieces. Right? So this is 0, this is pi, so this is 1, 2, 3, 4, 5, 6, 7. So my 7 pi over 6 is this angle here. And the reference angle to that is pi over 6. So it turns out that this guy is going to be plus or minus the sine of pi over 6. Now remember we have in that table, okay, so we have sine. Now you can do it in your head, right? Because you have that table For the sine, it's 1, 2, 3, where the 1 shows up under the pi over 6. You're going to take the radical and divide by 2. That's a half. Now, what sign do you take? S-I-N-G. S-I-G-N. Well, this is all students take calculus, right? Your sign is negative in this quadrant. So you take negative. So this is negative 1/2. So somewhere asks you, what is sine of 7 pi over 6? The answer is negative 1/2. Questions?
I have a question.
Yes.
All right. Can you just go over it one more time because I was copying that. I didn't get a chance to.
Oh, well, we have 2 more examples, or do you want to go over this one?
I want to go over that one.
Because sine is periodic, it repeats its values, right? So I know, given any angle, I can find some other equivalent angle to make it nicer, right? So this is the reference angle that's smaller, that's between 0 and 90 somewhere. Okay? So to figure out what that reference angle is, I need to figure out what is the smallest angle this makes with the x-axis. So I draw a picture. Draw my circle. Now this says I have 7 pi over 6s. Now of course, this is algebra class, you do realize that 7 pi over 6 is 7 pi over 6s. So I take pi divided by 6 and I want 7 of these pieces. So here's 0, here's pi. I'm going to divide it into 6 equal pieces. I can do that at the bottom as well. Now I want 7 of these pieces. So I literally count. Start here and count. 1 slice, 2 slices, 3 slices, 4 slices, 5 slices, 6 slices, 7 slices. So that means my angle ends up here. That is in quadrant 3. Last time we saw that all students take calculus. Means only the tangent and cotangent are positive here. All other trig functions are negative. In particular, the sine is going to be negative. So in quadrant 3, we know here that the sine function is negative. We further know that this is the reference angle, which is a slice of size pi over 6. So hence I end up with the fact that sine of 7 pi over 6, well, this is just plus or minus sine of pi over 6. In fact, I can use the nice angles, the special trig angles, with certain multiples of these trig angles. And I pick the sine depending on the quadrant that that actual angle is in. And so here it's in the 3rd quadrant, the sine is negative, and so that's why I would choose negative sine pi over 6. This value we have memorized in the table from last week, that's a half. So that's your answer. Let's try another one. How would you do with this one? Cosine of minus 4 pi over 3. You want to try this one so you get it? Yeah?
Huh?
You want to try this one?
All right. All right. So I believe you break it up into 3 equal pieces.
Right, so this is pi over 3, so I'm going to draw a circle.
So it's 3 pieces on top and 3 pieces, equal
Right,
pieces.
because half is pi, right? The whole
Yeah.
thing is 2 pi's. So I break it into 3 pieces on top, 3 pieces on the bottom. Okay.
There's a negative, so I believe you go counterclockwise.
You go clockwise.
You go
clockwise.
You go clockwise.
Yes, so we
All right.
start, you always start at the positive x-axis,
And
and you
because you
measure
want 4
clockwise.
pieces,
So
you
what do we do now?
1, 2, 3.
Because you need to.
Yeah.
Wait, what?
Oh, you hit it 4 times. 1, 2, 3, 4.
You keep going around until you cut through 4 slices. 1 slice, 2 slices, 3 slices, 4 slices.
Yes.
So you stop there. Now you'll notice the reference angle for that is just this angle here, which we know is pi over 3. We also remember from last week that all students take calculus. You're all going to take calculus. So this here, the cosine is negative, right? Because only the sine and cosecant are positive. So my cosine of negative 4 pi over 3 is going to be equal to the negative of cosine pi over 3. Now, without looking in your notes, what is that? It's also 1/2. So this again is negative 1. Sine of 3 pi over 4. Oh, we didn't actually do the 225. Totally forgot that. So we do here. Divide into 4 pieces. So we have a circle, slice it in half, that's pi. You want to divide each pi into 4 equal pieces. So you can slice it in 2, then slice each half in 2. Same thing here. We want 4 equal pieces. What do we want here? We want 3 pieces. Start here, count, 1, 2, 3, boom. Of course, we know all students take calculus, and we have the reference angles here, which is obviously pi over 4. And so the sine of 3 pi over 4 is going to be positive the sine of pi over 4, which we would have memorized is radical 2 over 2. Now, let's do the 225 in one of these problems. So, I don't know. What about tangent of 225 degrees? Well, you can, in principle, you can do the same thing. It's just that the numbers aren't going to be that nice, right? The numbers are really nice with the theta, because you only have to like count in like little integer numbers. Whereas here, to do this, you have to count 180 things, right? You can also, with the degrees, it also helps to actually maybe write in some more numbers. So this would be 90. What would be over here? 270. Eventually here, this is equivalent to 360 degrees. Okay, so 225 is obviously somewhere between 180 and 270. So I'm not gonna like count 225 pieces of anything. I just know it's somewhere over here, right? So it's just a guess. So I'm just gonna call that 225. 225, right? Now, of course, I need to know what is the angle here.
So you would take 225 and subtract by 180 in order to find the reference.
Right, so now you would take your theta bar is going to be 225 minus 180, which is what? Which is 45? And so, also, we know that all students take crap. The tangent is positive in that place. So this guy is equal to the positive tangent of 45 degrees. And what is the tangent of 45? 1. It's 1, right? And you can know that from the table because you'll notice that the sine of 45 and degrees and the cosine of 45 degrees are the same value. And the tangent is just the ratio of these. So this is just positive 1. So degrees, it can be a little bit. You can use the same idea, but the numbers are going to be much bigger, right? It's nicer to work in radians. You have very small numbers. Yeah.
So I'm lost in that part with the all students take calculus because in one of the other questions you said it was negative, it was a t, and now you said it was positive. So how do you know when it's positive or negative?
Because of all students take calculus. These letters tell me who's positive and who's negative.
Okay, so say for example,
Right?
you
A
have-
means A stands for all. Means all the trig functions are positive. There are 6 of them. Sine, cosine, tangent, cotangent, cosecant, secant. Right? That means all of them are. Over here, the sine is positive. That's what the S stands for. So sine and 1 over sine, which is sine and cosecant, those are positive. Everybody else is negative. Right? If you move over here, the T stands for tangent. Tangent is positive, so the cotangent is positive, but everyone else is negative, right? And so on and so forth. So earlier we were measuring with sines and cosines. In this quadrant, sine and cosine are negative. That's why I said earlier it was negative. In this case though, I'm actually measuring the tangent specifically. And the tangent stands for T, it's positive here. Right? So it depends on the quadrant and the particular trig function that you're looking at. And that's a nice way to get the actual trig values for some weird angles. Not that weird, there'll be things you know how to do by hand. Yeah.
So if it were in the area of where C, would it be negative? Would tangent be negative?
The tangent would be negative, yeah. So if my angle ends up here, if you're looking for a cosine, it's positive. If you're looking for a secant, it's positive. But if you're looking for anyone else, it should be a negative value. Right, so our knowledge of reference angles and all students take calculus together can help us find trig functions at multiples of our special angles. Which, and again, once you get really used to this, you'll be able to do this very quickly. Especially if you can often do this picture in your head. Right, someone can ask, what's 3 power 4? Well, 3 power 4 is in the second quadrant. You'll be able to slice it in 4 slices in your head and figure out what quadrant this is. Then you can do that table in your head and do that. And so your friends can ask you, what's the sine of 3 power 4? It's just this. How did you know that so fast? Yeah. It'll take a little bit of practice, but it's actually not bad once you get the hang of it. Let's see where else. Did I mention everything I wanted to mention? So that's actually important. We'll get back to using that soon when we get to start. We're going to solve equations with trig functions. We're going to have graphs and want to find the intercepts, and these kinds of things will actually come in handy. That being said, let's actually talk about, so this is mostly 5.3. Now let's actually talk about the graphs. Now, technically you only need to know about the graphs for the sine function and the cosine function and transformations of them. I'll mention some of the other ones though. You don't have to focus on them too much. So the graphs of the trig functions. Again, we can start with the unit circle. And say we're looking at, let's say the sine function. So let's say I have a function y equals the sine of x. So x is the input, x here can be thought of as some angle that I'm plugging into a function, and the y is going to be the output of that function. On the unit circle, there are some nice values that I can immediately get. First of all, I will know the values at the special angles. So at pi over 6, I'll know the value at, these a little bit in different color. Let's do pi over 6 in white. And let's do pi over 4, that's in green. And let's do pi over 3 in red, right? I automatically will actually know what values the sine function will actually take here, right? So once you're at this coordinate, your sine function will give you the value 1/2. Once you're at this coordinate, the sine function will give you the value radical 2/2. Once you're at this coordinate, the sine function will give you the value of radical 3/2. There are other values that we can tell immediately from the circle. So for example, at the points where we hit the axes, those are nice points to know. Now of course we already know the coordinates here. This is the coordinate 1, 0. This is the coordinate 0, -1. This is the coordinate -1, 0. This is the coordinate 0, +1. We of course remember that the sine function, this tracks the y value along the unit circle. So we can actually start to figure out here that your sine at 0 will be 0. Just looking at the y-coordinates. Here, your sine of pi over 2, which is 90 degrees, will actually be 1. Here, look at the y value. The sine of, here this will be pi, is actually also 0. And look over here, and the sine of, if you look in terms of radians, this will be 3 pi over 2 is actually minus 1. Right? And so you can plot a bunch of points here. So when you're looking at the sine graph, you can start to plot points. And then, well, we're not going to do that because someone has already done it for us. So I'm pretty much going to tell you what the answers are. Plotting these, and of course painstakingly plotting other points. We obtain the following. This is the graph of the sine function. So here I can think of that as the x and that as the y. And again, x here I'm thinking specifically as the angle I'm plugging into the sine function. I notice it hits 0 when we're at 0. It also hits 0 when we're at pi. It also hits 0 when we're at 2 pi. When we're at pi over 2, it actually hits 1. When we're at 3 pi over 2, it actually hits minus 1. So I know it goes here, it goes here, it goes here. And of course, you'll notice here that if you look at the y values are gradually getting larger until they peak here. They get smaller until they hit here. They get smaller still until they hit here. And then they start increasing. If you only look at the y coordinates. And so that will tell you that the function increases until it hits a peak. It'll then immediately start to decrease until it hits this. It'll continue to decrease until it hits that, and then it'll continue to go here. Right? So you can get the sine function in several pieces. So you're looking at, say, this part right here would correspond to this part of the graph. And this part right here would correspond to this part of the graph. This part right here would correspond to this part of the graph. And then this part right here would correspond to this part of the graph. Now it's supposed to look a lot smoother than I just drew. It's hard to draw things on the blackboard. Now, remember that this goes around in a full circle. But what it does after that is it just repeats all its values. So you end up having this pattern repeating forever going back that way, and this pattern repeating forever going back that way. But this here between 0 to pi, that's called the principal period. Right? So if you want to draw a sine function as an example, you usually stop between 0 and 2 pi. Okay. Now, ultimately we get the following. In the same way you can do this kind of analysis for the cosine graph. Like this. So the graph of y equals sine of x. Just sketching the principal period. between 0 and 2 pi. It'll look like this. It's a wave, and this exact pattern just keeps repeating forever. But here's where 0, here it's at pi over 2, here it's at pi, here it's at 3 pi over 2, and here it's at 2 pi. Now these are coordinates on the unit circle, which means it'll never get larger than 1, and it will never get smaller than -1. Your sine will oscillate between these two values in this particular pattern. And your cosine is very similar. Here we just track the x coordinates instead. You'll get a very similar pattern, except it starts a little shifted away. It does that. So here's at 0. You'll notice that on the unit circle, your x coordinate is 0 when you're here. It also will hit 0. It's 1 when you're here. It'll hit 0 on the poles. So it'll hit 0 here at pi over 2. It'll also hit 0 at 3 pi over 2. And here it will be pi. And it'll hit a peak again at 2 pi. Now, from now on, these are now graphs that you just know now, right? And when I say you know these graphs, I mean you really know these graphs. After today, you should be able to draw these graphs and put in all these points without even thinking about it. Just like someone say, sketch x squared. You can just sketch x squared. You don't really have to think about it. It's kind of like a knee-jerk reaction. That's what these graphs should be for you now, right? So this is now added to some of the basic fundamental graphs that you should know. So you should know how to sketch y equals x, y equals radical x, y equals x squared, y equals x cubed, y equals absolute value of x, y equals ln x, y equals e to the x, y equals sine x, y equals cosine x. Okay? These are now it's in your basic graphs repertoire, right? These are now a part of the graphs of functions that you should be able to do literally without thinking. You should waste no time actually think. Someone asks you, sketch sine. What does it look like again? You're messing up, right? Once you do that, you're messing up. If you have to think for a second before you start drawing these, you are messing up. Make sure you know these graphs. Quickly mention these similarly. Right, again, by looking at the unit circle and measuring nice functions, you'll realize that the tangent graph has this particular pattern. This guy has asymptotes at pi over, multiples of pi over 2. Right? So it'll hit another one at 3 pi over 2, it'll hit another one at minus 3 pi over 2. There are some other interesting things to notice. It'll hit 0 at 0. It'll also hit 0 at pi. It'll hit 0 at minus pi. And it'll hit 0 at minus 2 pi, etc. So now what you need to realize is that these particular points, and the reason why you have asymptotes here is because tangent is sine divided by cosine. So you'll notice that this function is undefined whenever the cosine is 0. The cosine hits 0 at multiples of pi over 2. Pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, and going backwards. Minus pi over 2, minus 3 pi over 2, minus 5 pi over 2. So all of those guys, you hit a division by 0, your function cannot touch these lines. Since it is sine on top and cosine on bottom, whenever the sine is 0, the tangent will also be 0. And you'll notice from here, sine is 0 at 0, pi, 2 pi, 3 pi, 4 pi, 5 pi, and then going all the way back, minus pi, minus 2 pi, minus 3 pi. In fact, sine is 0 at every multiple of pi, while cosine is 0. I'm going to write down all this because it's stuff that you should know. Cosine hits 0 at every odd multiple of pi over 2. Right? Now, once you're getting close to these edges, you're emerging to division by 0. You end up having some number being divided by a very, very small number, so your number starts getting huge, and ultimately you have your graph going off to infinity, and then down to negative infinity. So this is the principal period of the tangent, and again, this pattern repeats. right? That repeats forever, right? So this one has situations where it cannot touch, and that's because it's a ratio. It has to avoid division by 0. Okay, so notice that. Now, here's again something cool. I can now think of what would the cosecant and secant look like. Now, I would leave these alone in your notebooks. If you want to re-sketch these, you can, but I would actually re-sketch them and then write on top of them what I'm about to write. Or you can just write what I'm about to write and ignore the rest, because I'm just going to show you how they actually work. So let's say I wanted to do y equals cosecant, which is 1 over the sine function, and y equals secant, which is 1 over the cosine function. Okay? Now again, this guy has to avoid division by 0 whenever the sine is 0, right? So every time the sine hits 0, this guy is going to have an asymptote. So you'll have one at pi, you'll have one at 0, you'll have one at 2 pi, you'll have one at 3 pi, etc. Right? And this graph will actually continue going over here. Now, of course, whenever your sine hits 1, your cosecant will also be 1, because it's just 1 over 1. So your cosecant graph actually hits these points. What does it do? Well, the edges tend towards division by 0, so your graph is going to kind of have to avoid these lines. It'll actually shoot up. And it'll shoot off to infinity. It'll never actually touch this line, but it'll approach it. Similarly over here, we'll go down. And that pattern will repeat. So then you'll have another part here that goes up. Right? So it'll look like a bunch of parabolas, very skinny parabolas, both positive and negative ones, extending forever, where their vertices are always on the point, on the value y equals 1 or negative 1, whenever your sine hits 1 or negative 1. By a similar, so if you erase the sine graph, this is what the graph of the cosecant graph would look like. By a similar logic, the secant will hit 1 every time the cosine hits 1. And it will be undefined every time the cosine hits 0. And again, it'll go up like that. It'll go down like that. It'll go up like that. Then go down like that. So if you wanted to actually look at what those guys look like, you can actually just kind of erase these. So once you can get the sine and cosine, you can figure out the graphs of the others just by looking at what you're forced into by the arithmetic. Similar to this one, the cotangent, whenever this is tangent is 0, the cotangent is undefined, so it can't touch these lines. And it will actually just look like a shifted version of this. Technically speaking, you don't need to know these graphs, but we're here. Might as well I just mention them. We're going to do the sines and the cosine graphs in a lot more detail, though. I might also do the tangent in a little bit more detail, but that's kind of let's see. I have 2 minutes. Let's state some facts. Remarks. The graphs, you'll notice, give us many more values. For example, we know what sine and cosine were at 30 degrees, 45 degrees, 60 degrees, or pi over 6, pi over 4, pi over 3. But now, thanks to the graphs, if you look at the sine function, for example, looks like this, you'll start to notice some patterns here. So at pi over 2, the sine should give you 1. At pi, the sine should give you 0. At 3 pi over 2, the sine should give you -1. And at 2 pi, it'll give you 0. So you automatically now know 4 additional values, or even more. 1, 2, 3, 4, 5 additional values. So immediately we now know that the sine of 0 is 0. The sine of pi over 2 is 1. The sine of pi is 0. The sine of 3 pi over 2 is -1. And the sine of 2 pi is 0. In fact, we also know from the graphs that sine of n pi is 0, where n is any integer. Integer, remember, from the beginning of class, that just means a whole number. So sine of 2 pi, 5 pi, 7 pi, sine of 15 pi, sine of 26 pi. Sine of 1,352,412 pi is 0. Sine of any integer times pi is 0, right? Again, because this value just repeats, right? So you kind of know that. Needing to know where the sine function is 0 is super important. You'll also notice that the sine function will hit +1 at odd multiples of pi over 2, where it actually switches based on that. But this fact is pretty important to know. So these are all things that you should know, and I wouldn't memorize them in a whole new table. I would just by learning the graph, you automatically know these things. This is also a super important fact. So that's just something that you should also know now. You should know when the sine function hits 0. What are the x-intercepts for the sine function? All multiples of pi. You'll also notice something else, a concept that we spoke about a long time ago, but it's still relevant. Also, from the graph, you'll notice that the sine is an odd function. Remember what an odd function was? It's a function that was symmetric about the origin. You will notice that if you look at the sine function, pick an x value, it'll output some y value. If you pick the negative of that x value, it'll output the exact negative. It's kind of symmetric. So points here, I can rotate around the origin and hit points over there. Right? This means that sine is odd. So in particular, something that we also know is that if I take the sine of a negative angle, it's just a negative sine of the angle. That's something you should also know. That we know from the graph. So if someone were to ask me, what is the sine of -3 pi over 4? Well, that's just negative sine of 3 pi over 4. Pi over 4 means divided to 4 equal pieces. 3 pi would be in the second quadrant. Cosine is positive there, so it'll just be negative of some positive value, and that positive value would be radical 2 over 2. And so this is also minus radical 2 over 2 because of this. So I don't want you to mistake this for the fact that, don't think of this as you're factoring out that -1, because you can't actually do that in general. This is true because sine is odd. That's why it has this property. It has this property that you can factor out a -1 specifically, right? So if you have like sine of 2x, it's not the same as 2 times sine x, right? You can't factor anything out. It just works out, you can factor out specifically a -1 because of this property, not because of some algebraic property, it's because of how the graph behaves. Right? So this is a very important equation that you can use at any given time. So if you are working with the sign of a negative of something, just pull it out. You don't have to be bothered by that. I can make all the analogous comments with cosine. I don't think I'm going to get to the transformations of these graphs today. but we'll start that next time. That'll be a lot of fun. At least I think so. So now, if you're looking at the cosine graph, that looks like this. So remember, it hits 1 at 0, hits 0 at pi over 2, 0 at 3 pi over 2, it hits negative 1 at pi, it's 1 at 2 pi. So we immediately know a few values. Cosine of 0 is 1, cosine of pi over 2 is 0. You know that cosine of pi is negative 1. Yeah, by the way, all these values, these are things that you should just know now. So like it's just a thing that you memorize these as well. You can memorize these from the graphs. Eventually, after using the graphs up 20 times, you're going to eventually memorize the equations anyway. But these are eventually values that you should know cold turkey. Cosine of 3 pi over 2 is 0, and cosine of 2 pi is 1. In fact, some other important equations, we know that cosine of n pi over 2 equals 0, where n is any odd integer. Okay. So cosine of 3 pi over 2, 5 pi over 2, 7 pi over 2, 9 pi over 2, 13 pi over 2. Cosine of minus 15 pi over 2 is 0, right? These are things that you would automatically know. You also know that the cosine of n pi is 1 if, didn't even think of this as a piecewise function. This is a useful thing to know. It's 1 if your n is even, and it's negative 1 if your n is odd. That'll save you a lot of headaches in Calc 2, Calc 3, 392, differential equations. Eventually, 4 semesters down the road, your professor expects you to remember this, and so he's doing all these calculations. Where is he getting all these numbers from? He's doing this stuff in his head. But from now on, you guys should get this in your head and never forget it. Otherwise, math is going to just be a mystery. I don't understand how I got from this line to that line. Because sometimes you're having like all these trig functions, and then suddenly the answer simplifies to like plus 3. You're like, what? How did you get plus 3? You know? Because this, he's applying, oh, these ones are zeros, this part you can factor out a negative, that part you can do that. So yeah, you should know these, never forget them. Another thing, important idea is cosine x is an even function. You will notice that if you were to continue this pattern, pick an x over here, you'll get a certain y value. Pick the negative of that x, you actually get the same y value. The cosine is symmetric about the y-axis, so if I take the right side and I flip it, it falls right on top of the left side. Which means, lucky for us, that if I'm looking at the cosine of a negative angle, computationally, it's exactly the same as the cosine of the positive angle. I can literally ignore negative signs whenever I want. And that happens specifically because cosine is even. So if someone asks you, what is the cosine of 7 pi minus 7 pi over 6? Well, that's exactly the same as cosine of 7 pi over 6. That means divide pi into 6 pieces, count 7 pieces, that'll put you in the third quadrant. Cosine is negative, and it's radical 32. Because I did all that in my case. Now in Calc 2, Calc 3, 391, 392, your professor will be writing this stuff down and writing these numbers down. How does he know that? He has those tables in his head. He's not telling you, but that's what he has in his head whenever he's doing that. Still a little bit more time. Let's see what else I can squeeze out. Do I want to start that? Open that can of worms? No, you definitely don't want to do that, Jhevon. Here's something, some people like it, I don't particularly like it. Because believe it or not, I tell you guys to memorize a lot of stuff, but I actually hate memorizing stuff. I only memorize stuff when it's super important, so when I tell you guys to memorize stuff, you should consider it super important. So there's a slightly larger table you can memorize that will have extra values in it. I don't do it because if I already went through the trouble of memorizing the graph, I'm not going to memorize the bigger table. That's just how I look at it. But some people might like it. So that table I drew for you earlier, with the sine theta, the cosine theta, you can actually do it extended a little bit. You can start with 0, right? And then you can do pi over 6, pi over 4, pi over 3, and you can throw in a pi over 2. So this is when you're throwing in degrees. This is 0 degrees, this is 30 degrees, this is 45 degrees, this is 60 degrees, this is 90 degrees. And believe it or not, you can follow exactly the same pattern, but start from 0. So 0, 1, 2, 3, 4. 4, 3, 2, 1, 0. You can take the radical of everyone. Then you can divide everyone by 2. Now, of course, 0 divided by 2 is just 0. Radical 4 divided by 2 gives you 1. Radical 4 divided by 2 gives you 1. 0 divided by 2 gives you 0. And so you can get these edges. You can get the 0 degrees, sine of 0 is 0, cosine of 0 is 1. You can also get the 90 degree part. Sine of 90 degrees is 1, cosine of 90 degrees is 0. So if you're into that sort of thing, you can extend the table a little bit more. I personally, I think my brain works a lot quicker if I just have 3 columns to worry about. If I want to worry about these guys, I actually think of the graphs. But the thing is, I do that so often that I kind of automatically remember these guys anyway. So I don't necessarily like memorizing a bigger table. That's just more information that my brain has to pull on in high pressure situations. And I try to keep it very simple. What you have to remember is that once you actually get stressed out over something, is that your high-minded, sophisticated brain skedaddles. It takes off, right? When you blank out on a test, like that's what happens, right? And it's just like your little animal brain, which is like in fight or flight mode. That's the brain that tells you, oh, there's a tiger chasing us, we better run. That guy takes over when you're under stress. So what you want to do is whenever you're learning something, one thing you want to do is you want to try to learn it as simple as possible. So simple that even your animal brain can, yeah, I get it, yeah. Sine of pi over 6, yeah, that's a half, got it. Right? You learn it in such a way that even if your complicated thinking brain runs and leaves you, your simple brain can still be in the driver's seat and you'll be fine, right? So let's try to memorize things in smaller chunks and it'll actually be better for you. And eventually, once your smaller brain is in the driver's seat for a while and things are going fine, you'll eventually start to calm down and then your high-minded brain will come back, right? But that's another reason. That's one of the reasons why sometimes when you walk out of a test, the answer immediately comes to you. Like, why didn't I think of that like 10 minutes ago? That's what happened. Your brain, with all the sophisticated knowledge, left you when you're in stress. Once you calm down, it comes back. So what you need to do, you need to happen in the test. How you do that? Learn something simple so that even if you freak out, you're still killing it. Once you kill it psychologically, you're going to start calming down. The knowledge is going to come back before you leave the room. I still could squeeze a lot out of this, but I guess we'll stop there. We'll start fresh on Wednesday with transformations of graphs, and that's going to be an important topic. There's definitely going to be a question like that on the final. There's going to be like one file that asks you to sketch a certain sine function that has manipulations done to it, or a cosine function. I'll show you how to do with those at the beginning of next class.
I see a sine de Remy. Oh, I believe that